Yeah, I've got nothing this week. So, entropy. Entropy is one of the three state functions that you're usually taught in general chemistry. And if you take it the old-fashioned 2-semester way, some people take it 3 semesters. I don't know how that works. I should look that up one day. But most folks, you're probably doing it 2 semesters, General 1, General 2. Entropy is usually taught in General 2. The first one you were taught way back in General 1 was enthalpy change, delta H, which comes up again this semester. The other one is Gibbs free energy. We'll talk about that a little later at another time. But entropy is a measure of disorder. Why we chose to measure disorder instead of order is kind of a relative thing, but I don't know. I guess scientists are just all emo at heart. But it's usually symbolized with the letter S. Why we picked S, there's a reason, but you guys can Google that on your own. And it's usually measured in joules per Kelvin, how much energy is being transferred per Kelvin as this disorder is occurring. So like enthalpy, a lot of times we look at entropy in terms of how it changes in a system, and for us, our systems are usually chemical reactions. So if entropy increases during a chemical reaction, then that should be a positive change in entropy, a net increase in entropy. And in chemical systems, there are a lot of ways you see entropy increasing, so the same ways every time. For one, as you change phases from solid to liquid to gas, entropy will increase. And if you think about it, that kind of makes sense, because when you're in the solid phase, earlier, either into last semester or beginning of this semester, for me it's the beginning of General 2, we talk about solids and liquids and kinetic energy. And when you're in the solid phase, everybody's pretty much motionless except for molecular vibrations. But when you get to the liquid phase, they start to move around more, have a little bit more fluidity. And when you're in the gas phase, they got lots of kinetic energy and they're just zipping around all over the place. So yeah, you expect entropy to increase as you go from a solid to a liquid to a gas. Think about it this way. If you think about, say, 1,000 cars in a mall parking lot, just still, versus 1,000 cars flying around on the interstate at 80 miles an hour, which seems to be the more disordered system. Don't let the chemistry throw you. We talk about disorder, it's more or less the same thing we're talking about that you're already familiar with. Likewise, when you dissolve a solid, you go from solid to aqueous phase. You go from everybody sort of not moving to now they're all swimming around in the solvent. That usually leads to an increase in entropy. But on the other hand, if you dissolve a gas, that usually leads to a decrease, because gases tend to have the highest entropy. Again, lots of kinetic energy zipping around all over the place. But once you dissolve them, now they're confined more in their solvent, so they can't zip around as much. And finally, if you increase the temperature, that usually translates to an increase in entropy. Okay, again, higher temperatures, things usually move around more. More kinetic energy, which we talk a little bit about in the gas chapter, which is probably back in chapter or General 1 for most of you guys. Usually right before or after we introduce Thermochem, but that's another video. And for chemical reactions, a lot of times you can predict what's going to happen entropy-wise just by looking at the equation. So, for example, let's take a look at the combustion of butane. On the left side, we have 15 moles of reactant. Over on the product end, now we have 18 moles of stuff. Now, it's still balanced. You got the same amount of matter on both sides of your reaction, but it's packaged or distributed in different ways. You go from all your matter being in 15 moles of things to everything being in 18 moles of things. Again, going back to the car analogy, imagine 40 people driving around in 10 cars, 4-door car, or imagine all 40 people riding around in their own car. So you can which one's probably going to be the more chaotic. So since our matter is being distributed more, probably what's going to happen is entropy is going to increase. But for this example, everybody's in the same phase, and everybody's in the gas phase, which again, like we said before, has the highest entropy. But let's change water from a gas to a liquid, which I know probably isn't going to happen in a real combustion, but bear with me. Now, in this example, all right, now we have 15 moles of gas, but on the product side, we only have 8 moles of gas. Yeah, sure, we have a total of 18 moles of product, but some of that product is now been transformed into the liquid state, which usually has a lot less entropy than things in the gas phase. So just looking at how things are going phase-wise, and keeping in mind that gases tend to have the highest entropy, since we're overall losing some things in the gas phase, that probably means that entropy is going to decrease. But like we do a lot of times in chemistry, we can actually calculate stuff because we're scientists and we like to do that. And there's a way you can actually calculate the entropy change of this reaction. And you use these things called standard entropies. Basically, you're calculating how much entropy something has, per mole. Because unlike enthalpy, you really can't calculate the enthalpy of how much enthalpy something has, but you can calculate how much entropy it possesses, which deals with some other stuff, and we won't go off on that tangent. There are other tangents I can go on. But yeah, we talk about that in the third law of thermodynamics, other places in this chapter. But for now, just you can measure how much entropy something possesses. And usually in the thermodynamic chapter, there's this big table of standard entropies, usually measured at 298 Kelvin. And a lot of major publishers' textbooks, there's a huge appendix at the end that has a bunch of compounds and elements, and it has entropies, enthalpies, and Gibbs free energies in one big giant table. So the way we use standard entropies to calculate the enthalpy change of a reaction is you sum up the total entropy on the product side, subtract the total that you see on the reactant side. And if that sounds familiar, the product minus reactant thing, it's because if you think back to when we introduced enthalpy change, one of the ways you could calculate the enthalpy change of a reaction was pretty much the same way, using enthalpies of formation. And you're going to do something really similar with Gibbs free energy. We talk about that guy later on. Right. So going back to our first combustion of butane reaction, where everybody's in the gas phase. If you look up the values, the standard entropies of everybody in this reaction, you're going to get values that are somewhere like this. They may vary a little bit from book to book. So again, you just take the total on the product side, subtract the total on the reactant side. But just like we did with enthalpy change and enthalpies of formation, you got to remember these entropies are given per mole, kind of like the enthalpies of formation were given per mole. All right. So you look at this equation with carbon dioxide, for example, you have 8 moles shown in the equation. So you have to multiply each value by its respective coefficient. Unit-wise, this means the mole unit is going to cancel out, and we're going to get a value in joules per Kelvin. And I'm going to leave the units out just to save some space. But once you subtract the total on the reactant side, you get a net difference of 310.6 joules per Kelvin, which is a positive value, just like we predicted it to be. But what about the example where water is in the liquid state? So all the values are different except for water's, which is now 69.9. Going back to what we said earlier, notice that the gaseous version had a higher value than the liquid version. And again, you take the product total, subtract by the reactant total, you're going to get a value of negative 877.4, and which is, we predicted it to be negative. So I've done a lot of these reactions, trust me. And I don't recall ever running into an example where what we actually calculate differed from what we predicted. So this is one of those few times where you can play the whole does my answer make sense thing that people sometimes try to teach you in like test taking or homework, classes about taking classes. If those are still a thing, I think they are. Does my answer make sense? You can't always do that in Gen Chem. A stoichiometry, I got 8.5 grams of this stuff. Does that make sense? I guess. But here you can kind of do that. You got a negative value for your entropy change, which is what we predict just by looking at the equation. So we'll do one more. Now let's look at the reaction between silver ion and chloride ion to give you silver chloride. So it's a precipitation reaction. And precipitation, that's the opposite of dissolving a solid. And earlier we said that when you dissolve a solid, the entropy should increase. Here we're doing the opposite, so it should be the opposite. The entropy should decrease. If you want to check our prediction, we look up the standard entropies of these three guys, take the total on the reactant side, subtract the total on the product side, subtract the total on the reactant side. I may have done that earlier too, said product instead of reactant, but I don't know. I'll find out when I edit. But you take the difference, and that gives you a entropy change of negative 33 joules per Kelvin. So barring a math error, it looks like we're at least on the right side of our number line. I guess technically the left side is the negative side, but you know what I mean. We predicted a negative value. We got a negative value. So barring a math error, our answer makes sense. And the only real math error you can make is just adding when you meant to subtract or vice versa. So, but as long as you're careful about that, math-wise, it's not too tough. So that's it for today. I know it's a quick one. Sometimes I could do those. Sometimes I just blab a lot at the beginning and the end, like I'm starting to do now. So I don't know. I'll shut up. See you next time.